Okay, welcome back. So let's see. So if you remember in the previous parts, basically we see how to deal with limits of a sequences which are given explicitly. So their formulations, basically their formula, basically are given explicitly. Now in this problem, this is not given explicitly; it is given recursively. And now we are try to, even if we don't know the explicit formula, we are going to try to find its limits, okay, without knowing the explicit formula. But this is a kind of a theoretical problem. So solution, so let's see, for part A, for instance, the first part. So let's try to understand. So we have a sequence given recursively, and we are going to prove something. And now we are going to really prove something. So mathematical proof. So actually, the thing is, we don't know. Actually, the idea is we do not know the explicit formula, explicit formula for an, but still, then we use another technique. We use another approach to understand, to analyze, if you like, to analyze limit of an. Okay. In the previous problem, basically, or I don't know, in the previous problems in question 1 and 2, we know the explicit formulation, but now we don't know it. We don't have that information, but still we can prove something. So actually, how to prove a statement. Okay. So actually, to prove a statement like this above, for instance, in part A, we need to show that, remember, we need to show that this statement, so an is less than 2 for all n. So we need to prove this statement in a mathematical way. So you can test it by using certain values, but this is not a proving. Okay? So to prove, so to show that actually, so to show this an less than equal this 2 for all n. So this is your statement, basically, is true. So we need to show that this statement is true. We use the method of induction. Use the method of mathematical inductions. Okay, induction. So let's see how to use it. So let me show it. So first we start with an initial step. Okay, so initial step. What is the meaning? Just check the first possible thing in your statement, which means that for n equals n. So let's check that whether the given statement is true for n equals 1. For n equals 1, a1 is given, right? So remember, a1 is given, which is 1. So a1 is 1 here. Sorry. So a1 is 1. And of course, 1 is less than 2. So this is true. So this is clear, no problem. So the statement is true. So the statement is true for the initial step, n equals 1. Okay, fine. So the question is, what about other steps? So you may check n equals 2, n equals 3, n equals 4, but where to stop? So you need to prove that this is true for all n, and you have infinitely many n. So you cannot check the infinitely many of them. And checking a couple of them doesn't prove anything. Okay? So the second thing is, actually we assume that, so this is the induction part, we assume that the statement is true up to some point for all n less than equal to k, up to some point, up to some point, up to some number k. And if you like, n is greater than 2, we already show it. And actually, now we need to show that with this assumption in hand, we need to show that it is true for the next step, n equals k plus 1. Okay, this is our aim. So we need to show that it is true. So we actually, if you look at carefully the statement. So we assume that the statement is true for all n up to k, some number k. And we need to show that it is true for the next step, for k plus 1. K is just some number. And just observe. So just look at the following observation. Let's see, ak plus 1. So what is ak plus 1? So by definition, this is just 1 plus ak divided by 2, right? This is just a definition, right? So here. So when n is k plus 1, just substitute n equals k plus 1, and you immediately see what we have here. And fine, but by assumption, this thing is, by assumption, statement is true for the case n equals k. Remember, so therefore, if you look at carefully, so we have 1, nothing changed, I didn't touch anything, but here, since the statement is true for k, n equals k, okay, the statement is true, then this is 2 divided by 2, because the statement is true exactly when n equals 2. Therefore, this part is less than 2. Okay, can you follow? So this part is less than 2. But what does it tell us? So this is just 1, of course. So this is just 2. So what we show that ak plus 1 itself is less than 2. This is what we want to show. This is our statement. Therefore, the statement is also true for n equals k plus 1. There is no restriction for k. Therefore, by induction, you prove everything. So by induction, and so by induction, the statement, what was it? The statement is an is less than 2 for all n. This statement is true. The statement is true. True for all n. Okay, maybe I should erase this. Okay, this statement is true for all n. Okay, this is a mathematical logic. So this is the method of induction. But we are not finished yet. So this is part A. Now part B, we need to prove something else. So we need to prove this thing. So let's see. Now this is our new statement, and we are going to prove it. And by using exactly the same idea. So let's see, part B. Now we want to prove, we want to show that an is always less than an plus 1 for all n. This is the statement we wish to prove. Okay, then use induction. So let's see, let's use it. So initial step, which was for n equals 1. For n equals 1, a1, remember, a1 is 1, and a2 is, what is it? 1 plus 1 over 2, by definition, right? So these are just by definitions. And so, what does it tell us? Clearly, a1 is less than a2. So the statement, i.e., the statement is true for the initial step, which is n equals 1, which is the case when n equals 1. Okay, so can you follow? And the second one, remember, now we have a big assumption. So we have let n equals greater than 2. Now we assume, because we proved the other part, so we just assume that the statement is true up to some point for all n less than equal to k. And now need to show, so we wish to show it is true for the case, the next step. If it is true up to some point, we need to show that, it's enough to show that it is true for the next step. Okay, so this is more or less the idea. Fine, so let's see, just observe. So we just observe that. So we just observe the following. So a k plus 1, by definition, this is 1 plus a k divided by 2. This is by definition. But as before, statement is true, already true for n equals k. Therefore, so let me write it down. Therefore, we have 1 plus, maybe I should specify like this. It is already true when n is k. Therefore, we have automatically inequality like this, because, right? So these are all. So because of this thing is true for n equals k, we have this inequality. But if you look at carefully, so let me just a second. So if you look at carefully, so this is just okay. This is just by definition. What is it? This is just a definition of a k plus 2. So what you have in total, a k plus 1 is less than a k plus 2. So it means that a k plus 1 is less than a k plus 2. What does it mean? I.e., the statement is true, is also true for the next step, for n equals k plus 1, right? So therefore, since k is arbitrary, then by induction, the statement is true for all n. K is arbitrary, right? K arbitrary, if you like, right? So by induction, this statement, what is it? The statement is the a n less than a n plus 1. This statement is true for all n. Okay, maybe if you are not familiar with the symbol, maybe write it down, for all n. Okay, so we prove it. So this is a mathematical proof. We are not going to check case by case. We use a mathematical logic. So we prove it. So actually part C, so for part C, so let's see. So we remember, we basically prove this part, and then we prove this part. Now here, if exists, find the limit. But let's try to understand what we proved so far. So in part A, here the part A, what we proved that actually it says that the function is bounded above, right? So, but in part B, so where is it? In part B, it says that basically function is what? Increasing. Remember the theory. So the theorem says that if you have a bounded function bounded above, and if your sequence is increasing, then it is convergent, right? So it is, so the limit exists. Okay. So therefore, So we just note that, okay, part A, so what we show in part A, so part A implies that an, so this thing is bounded above. So what we prove in part B implies that an is increasing. Okay, so these are basically so what we prove in part A and part B, and therefore, so by theorem, remember, by theorem, so an is a bounded sequence, bounded above, and it is increasing. So by theorem, limits an exist. Okay, since an is increasing and bounded above. Okay, so this is a kind of a theoretical problem if you look at carefully. Okay, fine. Now we ensure that limit exists, and recall that once limit exists, basically it is unique, right? So the once lim an exists, then it is unique. It is unique. Okay, for instance, say limit an is some finite number L. Okay, so this is some finite number. Okay, so limit exists. And then we really want to understand what is this limit, and just look at the definition. So the limits an, but by definition of recursive relation, this is just 1 plus an minus 1 divided by 2 by the recursive relation, remember. And but now clearly, here limit an is L. Of course, if you rearrange the indices, this a limit of a n minus 1 is also exactly the same number. So this is just the indexing problem. At the end of the day, n approaches to infinity. And so with this information in hand, this is nothing but limit 1 plus limit a n minus 1 and 2, and each limit exists. Each limit exists. Therefore, we can, separate this operation. But now this is just, okay, 1 plus L over 2, because you have exactly the same limit here. Therefore, if you do the algebra, remember, you start with L. So this is L itself. So L equals 1 plus L plus 2. Okay, so this gives that, okay, L is just 2. Okay, so the limit is 2. That's all. Okay, so be careful. This is a kind of a hard problem. We need to use the definition of the existence of a limit, or somehow we use a theory. You have a bounded sequence which is increasing or decreasing. So you remember the theory from lectures. In this case, you have a kind of a sequence which is increasing and bounded above, and that's all. Okay. Fine. So let's see. Next one. Okay, fine. So let's try to understand this problem, similar kind of problems. Now we have a sequence defined recursively. A1 is 1, A2 is 2, and we have a kind of a recursive relation here. So where is it? So maybe I should write it down like this. Here, so we have a recursive relation, which means that a term can be obtained by summing the previous two terms, right? And we have, so let's see what we have in the question. So assumption is this thing has a positive limit, and now we need to compute this. Okay, let's see. solution. So what is given? So the given information is, okay, limit of an plus 1 divided by an exists, and let's say equal to L, and it is positive. Okay. Fine. So this is given information. So this is basically what is given. Fine. And basically, we will use the same idea. Since limit exists, it is unique. And clearly, then we just observe that by definition of this recursive relation, so an plus 1 divided by an is just, okay, just use the definition, right? An plus 1 is equal to sum of the previous two terms, which is this, divided by, okay, an, fine. So what is it? This is 1 plus an minus 1 divided by an. But remember, so the limit exists. So the since limit exists, since limit an plus 1 n exists, it is unique. It is unique. And so actually when you change the indices, I mean, so maybe I should write it down like this. So an plus 1 an, but this is equal to L. But actually, if you rearrange the indices, so you just write down, for instance, an instead of n plus 1, we have n. Then we have the term, I mean the previous term, which is n minus 1. So these are the same thing. So limit exists, and therefore there is a limit, and so the observation is, of course, remember, so this is just, 1 over limit an minus 1, which is 1 over L, as L, okay, L is positive, remember. And therefore, when you go back, so this star, maybe I should write it down like this. Let's say this thing is called star, and rewrite star, right? So star, and the star gives the following. So from star, okay, from the equation star, let's see what we get. So we get the following immediate observation. So L is just 1 plus 1 over L. Okay, so that's all. L. Oops. Okay, 1 plus L. Okay, fine. And L is positive, remember. So L is always positive. And therefore, this equality means basically you have something like this: L squared minus L minus 1 minus 0. And therefore, so actually this is if and only if L is, so you have two roots by using, this discriminant and business, similar kind of argument. So you have this. You have two possible roots, basically. 1 minus, okay, square root 5 divided by 2. The other is 1 plus square root 5 divided by 2. But we don't want this part because, L is positive. Therefore, this is the correct one, right? So the answer is limit is that number. And those who are familiar with this sequence and familiar with this number, and this is a rather famous, right? This is your, famously called the golden ratio. Okay, and the sequence here is called the Fibonacci sequence. Okay, so for those who are familiar with those things, I mean, this is the famous golden ratio and the Fibonacci sequence. So that's all. I mean, this is more or less what this theory about. I mean, we use the same idea, existence of limits, and we have recursively defined sequence. By using this theoretical analysis, we end up with the numerical value. Okay, fine. So this is more or less the story. But before closing up, so I have some exercises, similar kind of problems, if you like. So these are from the book, I guess, but these are very standard. By using the same ideas, actually, for the exercise here, A, just use, okay, maybe I'm not going to write it down, just use the first, I don't know, first two questions, basically the first question, same ideas, try to write it down exactly this similar way. And here, okay, what is it? So there is this. Okay, and anyway, so it is written. So there is a n+1 written here. And for part B, just use the same ideas as we did in, I don't know which one, last two questions. Okay, so part A for the first half of the lecture, and for part B is for the second part of the lecture. Okay, fine. Thanks, and see you next week. Okay.